All right, so we are going to start today a new module talking about memory management and talking about the different notions that go into how the operating system manages memory. So we talked about synchronization, and last week our topic of discussion was deadlocks, and we still have just a few more things that we want to say about deadlocks before we move on to memory management. You'll recall that our discussion ended with deadlock avoidance. There's a V in there somewhere. So how do you do deadlock avoidance? What's the algorithm most centrally associated with deadlock avoidance that we talked about last week? The banker's algorithm. Okay. And the metaphor for the banker's algorithm is that an operating system is like a banker lending out loans. Okay. And the banker never lets loans go out that are all going to come due without having resources in place. Okay. And so with the banker's algorithm, you've got this notion of a maximum request. And from the start, processes state their maximum request for all resources that they're going to need. Okay. And if they do that, then the banker's algorithm uses a worst case analysis to decide if, let's assume right now, given the resources that have been allocated, given the remaining resources that are the maximum that each process could want, let's assume they all immediately ask for their maximum amount. Does that lead to a deadlock state? And if it does, then we don't allow ourselves to get in that state. Okay. We want to prove that the state we're going into is a safe state, right? Which is not just a state without deadlock, but a state that no transition in the resource allocation graph can lead to a deadlock. Okay, so that's what the banker's algorithm identifies for us. Is this a safe state? Do you remember what the problems are with this approach? Okay, so who's you?
The process, I guess.
Okay, so the process, it's assumed, can tell us what its maximum request is going to be up front. Okay, and we don't know that. That's maximum requests are not usually known, okay, ahead of time. Additionally, the banker's algorithm and deadlock avoidance in general assumes that you've got a static number, or at least a predictable number and type and rate of arrival for processes. Okay, so a static number of processes, and that's just not true. Okay, and so basically what it boils down to is that you kind of have to be able to tell the future, and it's just not a reasonable thing to do. Now, that doesn't mean that we don't need to learn about this. A lot of this analysis, a lot of this insight goes into estimating workload when it comes to practical operating system deadlock avoidance. Okay. But one more thing that we might want to look at, aside from deadlock detection and deadlock avoidance, is deadlock prevention. Okay. Can we design a system that doesn't allow deadlocks to happen at all? And this goes back to the four requirements that are required for deadlock to take place, right? So I'll do 1, 2, 3, and 4. The first one is that we have to have mutual exclusion in place in order to support deadlock. we said before, look, mutual exclusion was our goal when we were talking about synchronization. It's what we want when we have resources that are allocated in a critical section. Mutual exclusion was supported fundamentally by semaphores. Okay, it's what semaphores do. Okay, but can we get by without mutual exclusion? Well, one thing we can do is try and use resource buffers. Okay, have lots of copies of resources, and even if we don't have enough copies of resources, we've got buffers in place so that the resources are available on a wait list. Okay, but this really just moves the problem around, delays the problem at best. That doesn't really solve the problem in general. The key idea, though, would be to avoid assigning resources unless absolutely necessary, and to make sure that as few processes claim resources as possible. Okay, so there's something to be said for good programming here. You guys ever wonder why we harp on when you open a file, you should eventually close that file? Replace file with any resource that your program uses, and you should only have the resources open that you need to have open when you need to have them open, and you should let them go other than that. Okay, and that will minimize the conflict that we have. Okay, but this doesn't really prevent deadlock. Right? We need mutual exclusion. It's like beer. It's the cause of and solution to all the world's problems. Okay, so mutual exclusion is both the solution to and the cause of our resource allocation problems. So it's not that's not it. Let's keep going. What about the second one, which is we have to be doing hold and wait, okay, in order to have deadlock. Okay, how can we get rid of hold and wait? What kind of thing can we do? Well, it could be that we just force all processes to request all needed resources up front, right, at the beginning. And they're going to request all the resources up front. That's one approach. What's wrong with that approach? Is that going to work? Well, doesn't seem like it. Why? Okay, so we said that before. This is the reason why deadlock avoidance doesn't work, because we don't necessarily know all the resources up front. There's a more fundamental reason why this is not going to help us, though.
Could be like what if you try to grab all the resources? Isn't that still going to cause like a block? Because the process would be the same thing both up front.
Yeah. So what you're suggesting is it's not true that everybody's going to get all their resources, going to complete their resource request block as an atomic whole, right? You may ask for all your resources up front, but you may be interrupted in the middle of asking for resources. And that still is a problem if some other algorithm, some other process runs and asks for all its resources as well. If you are blocked, or if you're ready rather, and you're still holding those resources, then it's a problem. Okay, so it might be that we have some kind of operating system imperative in place that asks for all the resources up front and does do that atomically, but still, the problem that was suggested in the back of the room is I don't know what my resources, what resources I'm going to necessarily need, or maybe how many of them I'm going to need. Okay. An alternative to this might be if I have to make a request, then I drop everything. Okay. So let's assume that we do force and do allow all processes to finish all their requests. Okay. All processes to finish all their requests. Now, if I am giving all my requests, okay, and I've got them, and then I need something else, then one approach would be release all those and then grab them all again, okay? And then you would have to block waiting on the process that has the thing you need to release it, okay? But you would not have held all those things through that entire wait time. Again, this isn't clearly a solution to the problem. Okay. Third thing, no preemption. That principle means that no other process can take another process's resources, can take resources from it. Okay. Yeah. Imagine if that were the case. Then we'd have another problem on our hands. Which processes should have preeminence over other processes when it comes to having resources? Okay. And that is not a question with an easy solution in and of itself. Right. So there doesn't seem to be an easy way forward attacking that condition either. Right. And so lastly is circular wait. I wait on you, you wait on me, or some combination of in-between waiting. It could be that we do this. We could number all the resources. Okay. So we've got all the resources numbered, and resource requests would have to be made in numeric order. By all processes. Okay, so what's that going to do? Consider that so this is process 1, this is process 2, and here's resource 1, resource 2, and resource 3. The only way we're going to get a deadlock is if I get this one, and then you get this one, and then well, let's just do 3 resources. We'll make it as simple as possible. And then I ask for this one, and you ask for this one. Okay. So in the order of request, P1 went R2, R1, and P2 went R1, R2. Okay. So the only way to get a deadlock is if there's some switching up of the order in which the resources are allocated. Okay. Does that make sense? So if this has 1 next to it and this has 2 next to it, and everybody who needs a 1 has to ask for the 1 before asking for anything bigger than 1, and everybody who needs a 2 has to ask the 2 only after if they got the 1, right? They have to be asked for in numeric order, then that will prevent deadlock. Yeah, it will. Okay, so should we do that? That's going to attack the circular wait. Should we do that? Will that work? Thoughts about the practicality of it? You're the operating system designer. I'm asking you if this is a practical solution. What problems do you see?
How would that work with opening files?
How would that work with opening files? Okay, I'm open to that. What do you mean?
Would each file be its own resource? Or?
Possibly. Would that work? What are the other, like, are you asking, like, if they're both reading from the same file, do we have to have internal resources for every file?
Do we have to like find some way to word on the resource request for files?
So what I would say is we're gonna say somewhere we're gonna give requesting files. Yeah, how many files are there, right? Should we say requesting files, any file? You know, so is a resource step, okay? Or should we say, hey, file 1 is a resource step, right? It's got a number, and file 2 has a resource step, it's got a number, and file 3 has a resource step, it's got a number. The second approach would be more fine-grained, right? The first approach might keep no two programs from having open files at the same time, and that's not a good idea, okay? So I think what you're touching on is that there are a lot of resources, okay? And even if we undertake giving every resource a numeric value, how should we assign those values to the resources? Okay, what resource should we make all processes ask for first? Okay, there's also another problem. So I'm taking other, let's shoot this idea down. What else is the other problem?
There could be a lot of overhead in keeping track of all these things.
Yeah, who's gonna force this? Make the resource request in numeric order. Is that the job of the process? Because we really don't want it to be, because programmers don't know what's going on. That we don't want to push this responsibility down to the programmers. Each individual programmer now has to make sure that when they're writing a program for our operating system, that they have a table on the wall that says all the process requests. Right? We don't want that. Okay. But if we don't have that and it's not the programmer's fault, then it's the operating system's job, okay? And so how does the operating system know? How does it pull ahead of time all the resource requests that are going to happen, right? It just doesn't, it's not easy to implement, okay? Yeah, under best circumstances, like ideal circumstances where everybody plays along, that's fine. But getting everyone to play along is a huge headache. You guys can't even see this, but getting everyone to play along is a huge headache with that. Okay. So what's the over under on this? There isn't a perfect solution. Now I know that doesn't make anyone happy. Like everyone wants to think that there's the right solution for how to do this. But this is a 400 level course, and we've already seen a couple of times where there is no perfect solution for how to do this, for how to solve a problem, and this is another one of them. The right solution is some mix of picking your poison, right? You can spool access to all resources, right? That'll attack mutual exclusion, but that has overhead. You can make processes request all of their resources initially. Not an elegant solution. You can take resources away once they've been allocated. Also not an elegant solution. Or you can order resources numerically. Not an elegant solution. Ultimately, what practically we end up doing is asking ourselves, how often is a deadlock going to happen in our kind of system, and how much do we hate it? Okay? It's something we have to live with. So if we don't hate it very much, and we've got a lot of resilience in recovering from deadlock error, and so deadlock recovery can be our friend, deadlock identification and recovery, or deadlock detection and recovery. And we don't mind like restarting a process, okay? and these processes are running all the time. When they get into deadlock, we just restart one of them automatically. Usually that's what we end up doing, not worrying about deadlock too much. But if we have a real-time system or a critical system, then we might start implementing some or all of these approaches to try and limit the number of deadlocks that we're going to run into as our system progresses. Okay. All right, ask me questions.
It's like deadlock is kind of random.
It is. It is. The condition that identifies deadlock is not random. But it's not like we can predict when it's going to happen, right? Except under like toy circumstances where it's like, here's these two processes, and we know that it's going to be request, release, and request, release. Oh, look, there's a deadlock there, right? But deadlocks tend to come up when there are 50 processes and some 30 of them accidentally get into a deadlock situation. Yeah. So it's a real problem. It's a real problem. 30 processes are all deadlocked. Luckily, you might only have to restart one of them to break the deadlock, though, right? And so that's one good thing about deadlocks is just pick a process that doesn't seem to be running, have something in place that says this process has been blocked for a long time, kill it, start it over again, you know.
The way it's actually handled at the OS, is it just
sometimes, yeah. Well, yeah, sometimes, yeah, yeah, because it's relatively simple to detect deadlock, and so once you know you're in a deadlock state, it's much more difficult to roll back from the deadlock state, though, right? But if you start nuking processes, here's a process, all right, we're going to stop that one, and we're going to send it out, or maybe kick it back to new, right? And just let it run again, then that might break our deadlock. And if it doesn't, then we'll pick another one and try again. Any other questions? So this is an open area of research in operating systems, by the way. Anytime I tell you there's no optimal solution, it's an opportunity for you. All right. Let's do our next topic. This is also the next chapter in the Xi book. And it's a huge topic in operating systems. And this is really just a survey class, so we're going to hit the high points on memory management. Okay. It's unfortunate that history has left us with two meanings of the word memory. Okay. In the first case, often what we mean when we say memory is we mean the RAM, the random access memory. Okay. How many of you have ever held a RAM chip in your hand? About half of you have. Okay. If you open up your computer, usually there's at least 2 slots, right? Sometimes 4, and they have little arms on the end that hook onto the RAM, depending on what kind of RAM it is. When you seat it in the board, you're looking on the board. It's just a chip, looks kind of like this, right? And it's got a bunch of square rectangles on it. Again, depending on what kind of RAM you have. Sometimes there's just one cover over them all, right? But it's about this size, and it has connectors at the bottom. That's your RAM. It's called RAM because it is random access memory. You can access any memory location anytime you want to. This is an example of fast memory. Okay? In fact, the only memory that is faster to access, read, and write than RAM is the cache memory. Where'd you go? The cache memory that is on the CPU itself, right? That's the only memory that's faster than RAM. RAM is where the programs exist. The instructions exist. Instructions and data exist when the processes are running. Okay? It's also volatile. Okay, what does that word mean?
Wasn't it a state when it loses power?
Okay, when the power's off, the memory is wiped. Okay? Turn the power off, there's nothing left in RAM. It goes away. There's also disk, right? Memory that gets written out to the hard disk or the solid state drive or the persistent memory, persistent memory type here, your SD card less often, or your USB drive less often. Okay? This is relatively slow memory. Okay? In the fetch, decode, execute cycle, right? Fetching from the disk is the bottleneck. Everything else happens tens or hundreds of times faster than spinning up the physical disk or reading to, it's not as true for SSDs, but still reading a location on the SSD and pulling that data word for word into RAM. Okay? That's the slow part of the computer. It's the bottleneck. The processor's way faster. RAM is way faster. Getting information from the disk is the slow part. Okay? And it has always been that way. And it will probably keep on being that way. It is, however, non-volatile. Classically speaking, RAM is expensive, right, in a per byte, right? And disk is inexpensive. Again, these are general. This is a general assessment per byte. This is for storage, long-term storage. And long-term can mean from process execution to process execution, right? RAM is for temporary storage. It's just where the instructions and the data go when we are running the program, okay? This is high capacity. We're talking on the order of, hundreds of gigs or even terabytes of data, okay? And this is data constrained. Not much space in RAM compared to the amount of space on the disk. Okay? I see some confused looks. Can I clear up any confusion? Any questions? All right, so we mean both of these things. We mean both of these things when we are talking about memory management. Okay? We're going to use both of these different kinds of memory when we're the operating system. We're going to refer to this as physical memory. Okay, as physical memory. And this is a lot of things, but disk, one of the things it does is store what's called virtual memory. Okay? Got to remember, physical memory is fast, it's volatile, it's expensive, it's data constrained, right? But it's kind of like close to the CPU. Doesn't take long to read data from that to the CPU. You can be done at the speed required for the CPU to not have to wait on the memory, okay? Not true for the disk, which is where the virtual memory gets stored, okay? So what actually is RAM? What is physical memory? AKA RAM. It is hardware that stores a linear sequence of bits. These bits are grouped into words. All right, so what's a word? Word is the smallest addressable fixed size unit of data, usually 4 bytes, but sometimes more. 8 bits in a byte, 4 bytes is 32 bits. So sometimes it's 8 bytes, especially if you've got a 64-bit system. But it doesn't have to be that much. It could be 1 byte, for instance. It's all in the architecture. So then there are physical addresses. Okay? And these are integer values between 0 to n-1 that identifies each word in physical memory. Integer values 0 to n-1 that identifies each word in physical memory. Okay? Each address comprises a fixed number of bits because that's each one is 1 per word. Okay? And so words have a fixed number of bits, and so the physical addresses have the same fixed number of bits. The addresses themselves, though, are also made up of some number of bits because they're numbers, and so it works out to if n equals n being the number of words that you have in your system. If n equals 2 to the k, then k is the number of bits required to address each one of those addresses. Okay, so this might be 8 bits long, in which case you have 2 to the 8 total address locations in your physical memory. Okay? All right, any questions about that? So it's been a while, and I didn't come up through this degree program, but I recall that a lot of you have not had architecture at all yet, right? Or any computer logic, or I don't even know what we call it. Is it called architecture here? You guys haven't done any of that? Okay, so computer organization. Okay. Did you guys look at like ALUs and half adders and full adders and that kind of stuff? Okay. All plays into this, right? All that stuff relies on being able to use space out of RAM. Okay. So RAM is just like a long series of addresses, okay, that are some number of bits wide, and each of the addresses is some number of bits wide, and each of them is uniquely addresses each location in RAM. Okay? And really, that's all RAM is. It's just a physical representation of values that are X number of bits long, right? And they are all represented by their address, which is K number of bits long. Okay? When we load a program into memory, we are placing the instructions and the data into some location in RAM. Okay? RAM does not necessarily, and probably will not, have just one program loaded in it at a time. Okay? Because we are going to have multiple programs in the system. And so to make use of the system as quickly as possible and make use of our total complement, our whole complement of fast memory, we're going to have RAM as full as possible, as much as possible. Okay? It's also true, though, that we do not have enough RAM to run all the programs that our computer runs. In other words, we don't have enough RAM to just keep our programs resident in memory. Okay? So you're going to have to wrestle with that fact if you're an operating system. There's just not enough RAM to run all the programs and keep them in memory all the time. So where do we keep them? And how do we move them? Okay? How do we move them from wherever we're keeping them into RAM? And when we take them out of RAM, where do we put them? Okay? Does that make sense? Because we need space. And it's not going to be that you can't run this program until these other programs end so that there's room for you in RAM. No, we're going to let you run as many programs as you want. And as long as our operating system does a good job and you don't have hundreds and hundreds of thousands of programs open at the same time, then we're likely going to make it look like all these programs are running at the same time, when in fact we can only fit a dozen of them in RAM at a given time. So we're swapping programs out of RAM and putting them back in all the time. Okay? And how we do that swapping or paging, again, we're going to see some more terminology and some more definitions here in just a second. How we do that has a huge impact on the apparent speed, performance of our computer. Okay? Does that make sense? We want to abstract the details of physical memory out from consideration by processes / programmers. Okay? Now, if you are writing object code, that is to say, you're programming a computer in binary, okay? Then you have to know where the instructions and the data are. Let's say you want to update a variable, you have to know what physical memory address that variable currently resides at in order to load it into a register, load a value into a register, execute the operation code for set, okay, in the CPU, right? And those of you who have taken computer organization know what I'm talking about, okay? You need to know where that is so that you can load those values in or write those values out to the specific addresses. That sucks. I want to work at a higher level of abstraction. So we've got assembly code. Maybe I need to know where things are, okay? Depending on what I want to do. So this is questionable. But definitely above this, any higher level language, okay? Any compiled or interpreted language should be designed so that I don't need to know that I'm not the only program that's running on the system, that I don't exist by myself in memory, and that I don't have memory to myself. Okay? Does that make sense? So you write a program and you say int I equals 5, and you write a function and you call that function foo I. Okay? Somebody's got to figure out, when it comes down to brass tacks, where in physical memory that location is. Okay? Somebody's also got to figure out where in physical memory the instructions for this function are. Okay? What entity is in charge of that? Programmer, are you in charge of it? Thank God, no. The operating system does do that. Yes, that is the correct answer. Think about another possibility, though. Some people might argue or might think, hey, it's the compiler who's in charge of that, right? The compiler turns this into operating code, right? Operating machine code, yeah? But the compiler does not care, does not need to know what the state of the program is when it lists the instructions, okay? From the compiler's perspective, our first memory address is 0, and everything comes off of that memory address, right? Memory address 0 is where we put our first code, first instruction. The next instruction goes in memory address 1. The next instruction goes in memory address 2. Some number of instructions later, there's data, and it's all dependent, it's all offset by 0, okay? Which will work fine if we can always be sure that we're going to load our program at memory location 0 in RAM. That's not a safe bet, okay? So if we have imagined that our memory goes from 0 to however big our program is, and our program gets thrown in physical memory at some location below 0, then all of our calls begin to be wrong, okay? The instructions point to addresses that are wrong. Okay, does that make sense? Yeah? So this is something that we have to fix, and it's the operating system's job to fix this. And how we fix it, well, there are several different methods. Okay? Alongside of physical address space, I said there's the concept of logical address space. And this is the address space that is the abstraction internal to the process. Okay? So it gets to start at memory location 0 at logical address 0 and go out to logical address m-1, where m is the total number of words required to store our process. Okay? This is not the truth. It is not a real place. It is not an executable situation. It's not the truth anywhere from the perspective of the computer or the operating system. This is just what the process gets to imagine the real world is like. Okay? From the process's perspective, I have all the memory I need. It's always available to me, and I use it like I want. Okay? That's kind of like the viewpoint of the compiler. So prior to execution, logical address spaces, so the logical address for a process, is mapped to some portion of physical memory and then loaded from the disk onto physical memory, right? So physical memory is RAM. That's the true facts. That's the ground truth about what memory is like for the computer, okay? What the fast memory is like for the computer. There are multiple logical address spaces. There's one for every process, okay? And when they're not in memory, they're being stored on disk, okay? And when I need to load a program, I take this whole chunk of logical memory, which is somewhere on the disk, and can be represented as 0 through m-1 address locations, okay? And I find a hole for it in RAM. So there's already a program running here. There's already a program running here. Oh, look, this is equal to m or less than m, where m is the size of this logical address space, okay? So I'm just gonna plunk this whole thing right in that gap, okay? And then I can begin executing that program. Except that the instructions in here think that my first address space is 0, when in fact, my first address space is whatever address that is. Yeah, does that make sense? And so all my calls to variables and functions, all those object code calls, are going to have addresses that are off by exactly this much. Okay? So how do we handle that? How do we fix that? There's two ways. Okay? There's two ways. We can do static relocation, sorry, and a word about this term, relocation. This is when I take a module of object code and either, for right now, let's just assume I take a module of object code and move it to a place in physical memory. This is relocation. So there's two types of this. There's static relocation and there's dynamic relocation. So static relocation is handled by a part of the operating system called the loader. And the loader goes through and updates all addresses before loading into physical memory. Okay? Look at instruction by instruction. Okay? Instruction by instruction. See if there are any memory addresses in there. Okay? And then add the offset. And then load the whole chunk in. Okay? Then there's dynamic relocation. And this address translation And what that means is it means converting an address that is written in the language of logical memory to the language of physical memory, okay, the translation, can be performed in real time in execution by the CPU itself. Okay? So what we do in this case is we say, take this chunk, and just leave the addresses alone and plunk it right here, okay? And then give yourself a dedicated register, right? Yeah, which I had to look the name up to be sure, but it is called the relocation register. Give yourself a dedicated register where you store the offset. Okay? And now, every time you execute an instruction out of this program, you check to first make sure that there are no addresses, and if there are, before you execute that add that relocation or that offset. Add the value from the relocation register. Thinking like an engineer, what are the pros and cons for these two approaches?
Taking a register just for that is kind of a big register.
Okay, well, I can see why you would think that, but yeah, I mean, it's only going to be the size of the address space long, or the size of the address size long, and you're always going to have some value in it because you're always going to be doing this when you execute programs. But what you are mentioning is that there is an overhead for every operation now, right? That is being executed at the hardware level, okay? So the CPU itself has been designed to check this first, then execute the code, then execute the instruction. And it has to be done for every instruction, okay? So there is an overhead when running a program to do that translation. As opposed to what? The other option is put the overhead where? Before you finish loading the program into physical memory at all, right? Do the overhead there. Okay, so under what circumstances would you want to do static relocation versus dynamic relocation? What kind of circumstances would you be looking for that would advantage one over the other? It could be, certainly. I don't think that's the main factor, though. I mean, certainly if you think, yeah, keep thinking. You're on the right track. All these instructions have to be translated. The question is not how many instructions have to be translated. All of them do. But when do they get translated, and when does it matter if we do it offline or online? This gives us an additional overhead when we are running the code. This gives us an additional overhead when we load the code. So if we are loading very little code, right, then we can save overhead when running the code by doing this. Okay? So under systems where we think we're going to not be loading code or processes into RAM that often, and that could be a kind of system where you've got a lot of RAM for the average process, or the process is long running, okay, we don't need to swap them out very much, then that could be an argument for doing static relocation. But if we're going to be loading and unloading programs all the time, and maybe not even finishing programs before we unload them, okay, then there's no need to do the overhead of statically relocating all the addresses, because we have no expectation that we're even going to execute that address this time that the program got loaded, right? And if we have to do that translation on every load, and we are loading and unloading programs multiple times before they finish, right, then that could be an argument for, instead, let's just design our system, our hardware, to do dynamic relocation, okay? Because we are unnecessarily translating instructions multiple times if we do static relocation under those circumstances, okay? Does the design decision make sense? The trade-offs on the design decision? And ask me questions. Have you ever wondered what? So if I've got main.cpp, and then you guys may not have programmed C++ in a while, but I teach 155 and 255 this semester, so it's all I think about. I've got main.cpp, and I've got the class implementation.cpp, and then I've got class implementation.h. How do I compile these three files together into a single program? Now, I could do a project, but the project takes care of what I'm asking you. So what does the project do differently than what I would do by hand? Like, what does the project do that I would need to do by hand if I didn't have a project? So,
it creates a makefile that is like a script that runs all the required commands for running the project.
okay, so I'm asking you, what's in that script?
The script basically contains all the commands that you need to get to the compiler.
So how many times do I need to call the compiler? I need to call the compiler. I need to do, for G++, it looks like this. G++-C main.cpp and G++-C class implementation.cpp, okay? And that -C means that we're not going to be compiling into an executable. Instead, what do we get out of these two? .o files. So main.o and class imp.o. Why are these called .o files? This is an object file. Yeah. These are what we would think of as object modules in terms of operating system. Okay? So these are source modules, and they could be code that we wrote ourselves, or they could be libraries. Okay? And then I take these two and I do G++, and I'll just do star.o, which just means G++ main.o and class imp.o. And that gives me a file that by default is called a.out, and that's the executable. Okay, does that sound familiar to you guys? If you put this in a project, all of this happens for you, and you're a lot happier, perhaps. But the operating system still needs to know about this. Okay, each one of these object modules has its own logical address space, right? So main.o presumes that everything in that module has a logical address. Its memory addresses start at 0 and go down. as does this, start at 0 and go down. Okay? When we compile them together, what we are doing is we are relocating these files. That's just a logical to logical relocation. Okay? So we would generally stack one of these on top of the other and then add the offset of the size of the first one to the addresses of the second one. Okay? So you've got two things go 0 to X and one goes 0 to Y. Now the whole thing goes from 0 to X and X plus 1 to X plus Y. Okay? And all the addresses in here need to be updated with that. That's a logical to logical relocation. Okay? The linker does that for you. Same process though. Now I've got a bunch of these. And I want to put this logical address space inside physical memory, which means I have to find a hole that's large enough to store all these addresses, and then I need to update these addresses to reflect where the program actually starts, what address the program actually starts at in physical memory. Okay? And that whole thing, by the way, is called the load module. Again, two ways to do that. You can do static relocation, you can do dynamic relocation. When I load, so let's say this is my RAM. You guys see this? Go back one. This is my RAM. When I load a load module in for the first time, I probably put it right here. Okay? And then maybe I'll put the next one right here. Okay? So this is one modules that's load module that's running, one process that's running. And here's another process that's running. Okay? And here's a third process that's running, and a fourth. Okay? All those are different processes. So what happens is these processes begin to finish. Okay? They begin to finish. And maybe they finish like this. Okay, so that one finishes. It's not like anything actually gets deleted from RAM, right? It's just that the operating system keeps track of the fact that this is no longer being used. It's no longer a process running here, okay? And then maybe this one finishes. So what you have left behind is a series of holes. And then there's the big hole at the end, right? Holes left in RAM, okay? These are non-contiguous, open/available locations in RAM. You need to run another program, okay? The operating system needs to figure out which hole to use. Yeah? Because what's happened here is that you've gotten fragmentation. And what we don't want to do, so when you defrag a disk, how many of you have ever actually sat and defragged a disk before? So like, it used to be something we would do all the time back before Windows NT, because it would really, a fragmented disk would really slow down searching. Because what ends up happening is that the disk, the operating system begins to break up files and just put a sliver here and a sliver here and a sliver here, just where it can. And then that means you have to look here and then skip over and look here and then skip over and look here. And the more slivers you have, the more you have to move the disk and the head, and the slower your file lookup is, right? This is different, but it's a similar concept, fragmentation, okay? You would like to keep all your load modules right next to each other, but you can't because they're gonna end in a quasi-random order, leaving holes behind. And you're gonna fill in these holes, but you have to pick a hole that's bigger, right, than the module you're about to load. That turns out to not be exactly true, but you're gonna try and pick a hole bigger than the module you're about to load. So the module you're about to load is gonna be smaller than the hole you have left behind. So you're gonna fill in all but just a sliver and leave a sliver of a hole there. And then you're gonna leave a sliver of a hole over here, okay? You got all these slivers, and this causes, over time, it just gets worse, and you've got more and more slivers laid in there. Okay? Does that make sense? So one of the things that the operating system has to do, and you can't pick up your objects and move them to the front, your object modules and move them to the front. Because if you did that, what would you need to do? Do what? Update all the addresses, which takes forever, and we only want to do it one time if we can help it. Which is why which is our argument against static relocation when we don't think we're going to get through with the program before it gets swapped back out. Okay, does that make sense? So what are the approaches? There's 4 of them. Different strategies. There's first fit, next fit, best fit, and worst fit. Now, the last one seems weird, but I'll tell you why it makes sense in just a second. First fit, start at the beginning of RAM and moving from, well, in my model, from left to right, but from low addresses to high addresses, from the beginning of memory to the end. Find the first hole that is equal to or larger than the load module that you're about to put in it. Okay? And we haven't talked about how those holes are maintained, but you can imagine that there's a dynamic data structure. It's not too hard to imagine one. A dynamic data structure that keeps track of where the start of each hole is and where the end of each hole is, and then therefore it's no big deal to figure out how big the hole is. Okay, in RAM. So first fit, look at starting at the beginning and of RAM and find the first one that fits. Now, what's the potential problem with that? And I'm asking theoretically, what's the problem with that? What makes a bad fit?
Calls for the fragmentation.
Okay. You have more, but just a little bit more than you need, right? Leaving behind a small gap. Yeah? Next fit. Don't go to the beginning. Go to where you are and then work your way down from where you are to find the next fit, the next hole. Why is that better than first fit? What's the rationale behind it? If you're always finding holes at the front, right, you're more likely to leave a huge hole at the end. You're going to overutilize the first part of your RAM, right? Fragment the first part of your RAM pretty badly, and then expand that fragmentation down toward the end of your RAM as you go along, right? So let's make sure we're looking at the whole RAM every time as we make our loop around the whole RAM every time as we're fitting these things in. Best fit, find the hole that is closest to the size that you need and use that. Now, what's the downside of that? What's the downside of that? Practically speaking. Well, you need to find a hole that is as close to the correct size as possible. So there's an optimization that's involved there. But there's an obvious problem with that. Okay, exactly. I think that's not the obvious problem, though. I think that's the unobvious problem. But yeah, you're absolutely right. The obvious problem is you need to find the optimal hole, which means you need to compare all available holes, right? So there's overhead in doing that, okay? But what's suggested in the back of the room is that I might end up with just a sliver. And I'm more likely to end up with a sliver if I pick the best fit, and that fragments out. I'm never going to be able to use that sliver until this program terminates or the program next to it, and that leads to more fragmentation of my RAM. So that's why this, although it sounds odd, is actually a good choice. Worst fit, because you want to pick the hole that leaves the biggest possible hole after you've loaded your module. Okay? So those are the 4 approaches. I wish I could tell you that one of them was determinedly better than any of the others. But a lot of testing has gone into this, and testing has not revealed that on average, any one of these outperforms the other in all cases. Okay? It is a factor, it turns out, of the average request size relative to the memory size and the variance of request sizes. That is the average load module size and the variance of load module sizes, right? So again, an open area of research. Build a better mousetrap on this, and the world will be at your door. Okay? All right, we're at time. We still got more to talk about. Your reading for this week is the chapter that goes over memory management. We'll finish the content up from that chapter next time we meet. Okay? Any questions for me?
Exercise 5 quiz thingy.
Yeah?
What is that over? It just seems like a quiz. Is that over? What is it over?
Just over deadlock.
Deadlock?
Yeah.
All right.
Yeah. Yes, sir?
Why is it a quiz and not a regular assignment?
What difference does it make? Because I had a set number of questions and I didn't want to have a bunch of paper. I didn't want to leave it up to you to copy your PDF and turn it in. Does that make sense? I mean, is it making it harder? Is it making your life harder because it's a quiz? So I confused a lot of you, but like I think it should be the same thing, because you should be able to answer them and then go back and change your answer before you submit your quiz. There's no time limit. And unless I misunderstand, you should be able to like even walk away from it and come back to it, right? So if you wanna write down the problems, write your answer out on a sheet of paper, and then transfer your sheet of paper all at the same time to the quiz, that's fine too. It's just from my perspective, I thought it would be easier this way. Am I wrong? Okay. It is open everything except don't cheat. I mean, it's not an exam, and it doesn't require honor lock. It's just an assignment. Okay? All right, I'll see you guys next week.